Hello and welcome back to Dan of Steel. Now this week what I'm going to be looking at is the heat treat oven. Now there's a lot of videos already available on the YouTube with some really great content, so I'm not going to go too much into the basic build side of things, but what I will show you today, so stick around, is some really good, what I think are really good anyway, insights in how to maximise the efficiency, get that performance out of it, and in the long run save yourself money with running costs too. So why don't we jump in and take a look, see what we've got. Okay, so the first thing I want to discuss today is putting together the heat bricks themselves. I use grade 26. That's what a lot of people go for on this type of build. You've got 23 as well, which a lot of people also go for. And what I want to show you now is a little trick and tip to what I think may make your life a little bit easier. I've not seen anyone else cover it before, so that's why I'm throwing it in the video here. It's something I think that will be of interest to you, but actually building the thing is so easy, a 10-year-old child can do it. So I let her, why not? So when you're putting these bricks together, I've seen and heard of quite a few people who say that the cement they use doesn't have particularly great bond, doesn't have very good adhesion. So I did a little bit of research into why, and what I came up with was something that actually makes sense when you think about it. Now, the cement that we use, obviously designed to be used at a very high temperature, it actually needs a little bit of heat to make it cure. So what I chose to do was, as you can see here on the video, I put my bricks together in a basic pattern, got things relatively tidy, and then just popped a little propane jet in there, brought the whole thing up to about 200 degrees, and I let that run for about 4 hours. And what it did was it took a little of the moisture out and actually helped bond everything together nice and tight. So that's top tip number one. So another thing my construction method allowed me to do was a little bit of testing before I went and put the whole thing together. And by doing this, it meant I could dial the kiln in a little bit and consider performance and efficiency during the process. And what you'll see here on the video is that I was taking regular temperature checks. This is with about 250 to 300 degrees inside, and I was checking the external temperatures to see how much heat loss there was. One key thing with the construction method I did of using a 10-year-old was obviously things weren't perfectly straight on the external edges, but that wasn't of concern to me because I was going to trim them up at the end or just before I built the metal frame for it. So long as the internal dimensions were correct, that's what bothered me, and I'll show you why very shortly, because I use an insert which is the key to making this kiln very efficient, to the point where I can actually, with 2,400 watts of power only, achieve 1,000 degrees in just 18 to 20 minutes, depending on the temperature outside, which I think you'll agree is pretty darn efficient. Now, I briefly touched on how I used a different material for the inside. So what you're looking at here is actually ceramic fiberboard. Now, my thought process was, from all of the testing I did with the temperature gauge and all the rest of it, seeing how much internal heat compared to the external heat, what I decided was these fire bricks actually give really good thermal mass. They hold a lot of heat, which is what I believe I saw. I'm certainly no master in thermal dynamics, but I kind of believe what I see. And what I decided I wanted to do was try and reduce the speed at which that heat was being lost through the brick. So I went for a ceramic fiberboard, as you can see here. Now the key to this was, as you can see, I've made little rebates like you would do, but every individual section I've left so it can be taken apart. And there's two reasons for that. One is it's very easy to work on and very easy to get your element installed in it. And two is, should you ever have an issue with your element, it's really quite easy. You just 4 bolts on the top metal lid that I've got, remove the metal lid, take off the cap sheet, which again isn't cemented on, and you can just take this apart and work on it at your leisure. So from the point of view of future-proofing it and making it more maintainable, this was the option that I chose to go with, and very much the key to why I can achieve such high temperatures in such a small amount of time. Now, there's a little look at it there. The board itself is quite expensive. I think I got, from memory, a 4 foot by 4 foot board, and it was around about £95, which you may think to yourself, well, this is starting to stack up a little bit now. But when you think my total build didn't come in at any more than £550 from start to finish for everything involved in this particular build, and then factor in running costs in the long term, this little expenditure now creates so much benefit in the long run. Well, I personally am very happy to do it, and I just want to share that with you here today. This particular picture here may be hard to see. I'll try and zoom in editing. But essentially what I'm trying to show you is, during the construction phase, putting my sides and my lid on, what I chose to do was use 2 inches of the ceramic fibre board for the roof piece. I think that's fine, and I used a 1 inch, as you can see there. I just welded some old mild steel together to create a riser section, because I wanted my thermocouple to be hidden from view. I don't like seeing things sticking out the top, and also, in my opinion, I'm less likely to knock it or bang it with something else in the workshop and create damage. So on the subject of thermocouples, I again did a little bit of research, and this is the more typical K-type one that people use with the little ceramic rings on it. And during my research, it led me to believe, and this is only reading what other people have said about them, that at the lower temperatures, this isn't necessarily the most accurate thing out there. And as tempering the blade is what I think one of the most important bits, I wanted that extra little bit of control. I went ahead and I sourced myself one of these stainless steel type thermocouples. It's a K-type still. You can identify a K-type by the fact that it has 2 wires for connection. That's the typical way of identifying them. And the nice thing about this particular one, if I just pop this one down, is that it's got a flexible top on it. So once that was inserted into the kiln through the very centre, I actually opted to go through the very centre there, so I had pretty much the most consistent reading I could possibly get through the top, and this section simply bends over and is hidden within the structure of the kiln itself, which I just think was a little bit more sleek and suits my needs perfectly well. Moving on, we're going to talk about the heating element here. Now, I did a little bit of playing around with the heat element too, and what I decided to do in the end was source, using Amazon, these coils. They're made from A1 Kanthal. It's 1.2mm thick A1 Kanthal, and the actual coil itself has a 7mm OD. So one thing I haven't heard people say, maybe it has been covered in videos before, is maximising the efficiency of your element itself. What you want to do is, when you get the elements, they're wound very, very tightly together, but you don't want them to touch at any point if you can avoid it, because it'll cause the element to burn out. So what you'll tend to do is put one end in a vise or a set of mole grips, and you'll slowly stretch it out until it's somewhere between 2 and 3 times the length that it was before, when it was all condensed nice and tightly. That will give you a really good, efficient heating element. So the other thing, which I believe has been covered, is when you want to make your termination points to go into, in my case, ceramic blocks, which is what I chose to do. Obviously there's a lot of heat being emitted here, is simply form a loop. So you stretch a piece of canthol wire out nice and straight, form a loop back on itself, hold this part where my fingers are with a set of mole grips, put this end into your drill, in your drill chuck, and just very, very slowly twist, and it will bind everything together like that. What it does, it gives you plenty of purchase when you go into the ceramic blocks for your connection points, but it also reduces the heat transfer through that element there as well, because you've doubled the thickness on it. So that's something that I think was particularly important. Now, coming out the other side of the termination blocks, or the ceramic blocks, I opted to use this insulated wire here to go to my PID wiring and all the rest of it, and this is fiberglass wrapped. So just thought I'd share that with you. It's something else that I did and just gives me that extra peace of mind. Now the element itself, I messed around. You can see on the picture here, there's my thermocouple coming right through the centre of the kiln, as I said earlier, and you can see on this particular side I had a play so that I could report back to you guys. Now I tried putting my heat element in this fashion here, which looks super cool. At the back edge you can see I went the opposite way. Now I'm bringing this video to you after having used this thing for nearly 2 weeks solid now, and I mean I've used it really hard. I've been running it for in excess of 6 hours every single day because I wanted to put it through its paces. Nothing against any other videos out there, they're all brilliant, but generally you see a build, you see them use it once and then they disappear, but of course we don't know whether things go wrong, and that's where I want this to be a little bit different. So the reason I've stopped at this point to show you this particular photograph is, when I did this, because I used the inserts, what I think I should have done, just for ease, because this coil here, right in the centre, as it's got hot and cold, hot and cold, hot and cold, has actually started to fold down. I'll show you that a little bit later. But it's, I believe, because I created so many undulations in here, it's created a little bit of tension within the element itself, and it's kind of trying to force its way out. So I would actually recommend not going this route, although it works very well, and going for the more traditional side to side, because you're putting less stress on the element, in my opinion, and it tends to stay in place a little bit better. However, I do have a very easy fix for this. As I said, this is a ceramic fiberboard insert, so really all I need to do, pop the top off the kiln, access this particular panel here, and what I can do is take some of this canthol wire, make a U shape out of it, drill a couple of holes through, and because it's an insert I can drill all the way through, slot that in so it works a little bit like a staple, and twist it on the back side and tuck it round, and that will actually hold that in. This is something that traditional fire brick you can't do. I know a lot of people have had issues with a traditional fire brick where their element pops out as well, and they try to make these staples the same, but of course it can only go so far into the fire brick. The nice thing with a ceramic fiberboard is, because it's only an inch thick, you can do a twist on the back side of it, fold that down. It's again very nice, neat, tidy, and in my opinion a far superior fix for a heating element should you encounter that particular issue. I suspect all that's happened because I cut these grooves by hand using nothing more than a knife and a small chisel, because it's a very, very soft material. When you do that, wear a respirator, by the way. Obviously this is ceramic fiberboard, you don't want to be getting that stuff in your lungs. But all in all, I think that's my top tips for you. If you're going to go this route, just bear that in mind. So, my workshop here in the UK offers certain limitations, like most workshops do. So we work on a standard 220 to 240 volt supply here in the UK, and most of our standard sockets are rated to 13 amps. So with all of this in mind, did the various calculations. You can actually, there's a very good calculator check on the Veg Oil guy, I believe his name is. Check him out, he's here on YouTube. But did a few calculations using his formulas, and it turned out that with a little bit of extra research again, if you're going to run for a long amount of time, like I do at times, as I say, in excess of 6 hours, it's not a good idea to max out these sockets. So with that in mind, I wanted to achieve somewhere around 10 amp draw so that I didn't burn the socket out, and it would mean I could use the thing pretty confidently that I wasn't going to cause a workshop fire, which I think we can all agree is a pretty important factor. So to achieve this, with the particular coils that I used, they're element coils, it transpired what I needed to do was achieve somewhere around 22 to 23 ohms. So what you can see here on the video, this is with everything installed. I'm just taking my fluke there, set it to ohms, and there we go, 22, 23 ohms. Now 22 to 23 ohms, what that means is my element is producing just under, literally just under 2,400 watts of power. So this is another reason why I've gone the extra step in trying to ensure maximum efficiency through my insulation and that ceramic fibre insert, because at 2,400 watts, although it's plenty of power, traditionally I think it's fair to say other people tend to spend anywhere from 40 minutes to an hour and a half to get to 1,000 degrees, whereas using this element, which as you've seen, very small element, only 7mm OD, I can achieve 2,400 watts. It's a 10.4 amp draw when it's at maximum, and it just works. It does exactly what I need it to do. It's actually quite close to a high-end purchased off the shelf kiln in its performance. Obviously I don't have all the fancy touchscreen stuff, but that is something that maybe I'll look into in the future. A little bit of Wi-Fi, it's not too hard to do with a little bit of head scratching, but I've kept this very basic for now because I think, like me, you just want something that gets the temperature fast, is nice and reliable, and gives you that peace of mind. So every time you do a quench, or every time you heat treat a blade of any description, you know you're getting what you need out of it. So that's the important thing. If you're in the UK, you want to be looking for approximately 22 ohms. Just as a matter of course, I will point out to you, with the elements that I bought from Amazon, I actually used 2 of them, and in the very back plate that you saw before, I put another ceramic block there and joined the 2 elements through the ceramic block. The reason is, one on its own wouldn't be big enough for the forge that, or sorry, for the kiln that I built, and 2, I wanted to balance my elements out. So where you're seeing a reading of 22 ohms there, what I actually had was 2 separate elements, one for the left side, one for the right side, which joined together in the back piece, and both were 11 ohms. So once I did the test there, you can see I came out 22, 23 ohms. It's very important that you try and keep things balanced like that as well. This part is something that I know has been covered by a lot of people who care anyway, and I'm going to cover it anyway because I feel it's that important. I'm pretty accident prone. So, safety. Right here is a kiln switch, and how I chose to incorporate mine, many people mount them on the side so that when the door shuts and opens, it makes or breaks the circuit to ensure that the element is safe. When the door is open, the element is off. When the door is closed, the element is on. Very, very simple. So how I opted to do it, I built the kiln itself in such a way that it's a freestanding module. I then built a subframe, which is this section you can see here. The subframe I built a foot longer than the actual kiln itself. I vented the subframe so that there's no heat transfer to the surface that I mount it on, which again, very important, and it does work very well, by the way. But what it also does, by giving me this extra foot at the front, it allows me to incorporate all of my control units here. Now, this particular cover, if you will, is just held on by 4 self-tapping screws just on either side here. So should I need access to that at any point, just take the screws out, pull everything forward, and I'm good to go. This kiln switch, I'll show you in a little bit of footage later on, or you'll pick up on that. All I did was I simply welded a plate to the bottom of the door here, so that as the door comes round, it depresses the kiln switch in the centre, which makes the element live, makes the circuit connect. Equally, when you open the door, the plate comes off of that switch and breaks the circuit, kills the element, so it's perfectly safe. Really can't stress this enough. If you are going to build one of these, I know you can just flick it on and off when you're opening the door, but it's less efficient again. It's just easier to keep the thing running, and that simple little switch there, which I think I paid £12 for, worth every penny. Safety first, guys. Moving on, I did a lot of testing in the early days, and this particular test, for the majority of, I used just high carbon steels, 1095, 1084, 15 and 20, you get the idea. And for many of my quenches, all I'm looking to achieve, typically speaking, is an average of around 820 degrees C. So I did some testing and I set a benchmark originally at 900 degrees, which is what you're looking at here. So with my initial attempt, if you will, at making this kiln as efficient as possible, I went to 900 degrees, and as you can see on the screen there, it took me 18 minutes and 55 seconds, which I have to say I was very, very pleased with. But I just wanted to see if I could do a little bit better. Now, the door, all it was at this point was sheet material with the fire bricks set in it. And I think we can agree it did very, very well. However, I then took a small insert of the ceramic fiberboard again. I used some of the paste from a tube. It's called furnace silicon, but it's not actually silicon. It's just a mortar, if you like, rated to 1300 degrees in a tube that you can depress using a skeleton gun. So I took a piece of the ceramic board, cut it to perfectly match the internal dimensions, and literally stuck it to the fire brick. I then went on and around that, on the external edges of that, I ran some self-adhesive fire rope. I then ran the tests again and found that I could actually, it was slightly different on different days. It has been very cold here some days, very warm other days. But as an average, as a benchmark, that simple little upgrade, I now achieve 1000 degrees, give or take 20 minutes. Which again, that blows my mind. For a self-build, for a DIY, absolutely made up with that. So another top little tip, consider that door, that one little insert in there from the ceramic fiberboard again, just slows that heat transfer. Obviously you've got the thermal mass of those grade 26, so they hold a bit of heat in and around the area so that your element isn't working stupidly hard. And I know that because anyone who's used one of these kilns, you can hear just a very faint buzz when the juice goes on, basically. So I can hear that flicking on and off, and use that as a guide. You can do the same, and that will indicate to you just how efficiently your particular kiln is running by how often you hear the buzz of the electricity going through to maintain that temperature. Something else for you to bear in mind, just thought I'd share that with you. here we are at the business end now. And a few more things I want to touch on, just in case you go down a similar route to this. Obviously your build is your build, you'll do whatever you want. But for my particular application, as you know, I've got my control box at the front here, I've got my door here, and I've got my hinges. The sheet material I used for the build was 1.5mm thick steel. With that in mind, there's a lot of weight in that door, and I was conscious that over time, all of that weight on this hinge mechanism that I made could cause the door to drop a little bit, and with the insert that I've now got fixed, which goes perfectly into the recess of the kiln itself, I felt it was very important that I made sure there was absolutely no sag, no drop, no room for error basically, because I don't want to damage the kiln, I want it to last. So what I opted to do was, I've got the control box at the front here, I simply made two, if you like, ramp systems, so that I can ensure every time I close that door, if it does drop over time, it will sit on these two ramps here, keep that door perfectly level, so I know the insert inside is perfectly lined up with the kiln itself, and it stops me damaging anything. I also went on and I upgraded my handle. Originally, there's a small hole here. I had a more traditional, if you like, I've seen people have it where you shut the door and just a couple of turns and that's the door locked in place. I personally didn't like that. I felt like it was a bit too much faffing about, so I got a simple clasp mechanism there, which I welded to a piece of tube steel on the top, so the retaining side is there and the actual clasp is on the front side here, and then a piece of plate coming out, hole drilled through, 100mm 10mm stainless steel bolt, and my spring handle there. Stainless steel again, it's been covered by other people, because what that does is it means that you don't have the heat transfer through the stainless steel like you do other things. And there you see, there's the insert, lines up perfect every time. Just another little thing I want to share with you guys, because long term it will help your oven stay in good shape. What we're looking at now is, as somebody on one of the forums that I go on has called it, is Kermit, my kiln, as I got her all painted up in my Kawasaki green that I like. And I just think this better shows what I was trying to say to you earlier about the plate, how that floats just above here, but it depresses that kiln switch. So when I push play on this video now, what we're going to see, obviously, it's up at 946 degrees. The temperature is irrelevant. I just wanted to check that everything works as it should. So kiln switch is depressed. That means the element is on. I go ahead, I open the door up, and what you'll see, that immense amount of heat there. There's that element running the proper way. And if you want to make those, I've done a quick video on it. Check out the rest of the videos on the channel. Very, very easy to make these knife racks. But you see it there, how quickly it cools down. That just goes to show that switch is doing exactly what it's supposed to do and keeping everything safe. So as I mentioned at the start of the video, I'm coming up for a couple of weeks of solid use with this kiln now. I'm going to show you a little clip here of me actually doing a quench on some 1084 copper Q my blade that I've recently made. And what I want you to look at is, I dropped this and broke it, but you see there's a couple of bits of that self-adhesive rope there, fire rope. I'm going to have to find a slightly better option. Those two particular pieces have come off. Doesn't appear to be massively affecting the use of the kiln, but I've got to find a better option than that. What I'll try first is maybe some 3M tape on the back side of it. You can see that piece has come off there and that piece has come off there. So I'll address that and see if we can't sort it out. But here's one of the blades into the quench, and you can see what a lovely consistent red colour that had all the way through it. That 1084 I was quenching at 815 degrees C there, nicely controlled. What can I say? I'm a very happy camper. You can be too.